Good afternoon, everyone. My name is Carolyn Thompson. I'm the Director of Philanthropy at the University Hospital Foundation, and I'm delighted to welcome you to our virtual expedition entitled To Walk Again. Thank you so much for joining us. I would like to begin by acknowledging that we are located on traditions and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continue to enrich our vibrant community. As Emily mentioned, today's session is being recorded. We will send the link to everyone who has responded to the invitation within the next few days. Please submit any questions that may arise during today's presentation through the Q&A button at the bottom of your screen. We will attempt to answer as many of your questions as possible during the Q&A session following today's presentation. Speaking of questions, we have one of our own that we'd like to ask. What brought you here today? Please participate in our live survey.
The results are coming in. We will give everyone about 10 more seconds.
Okay, so thank you, Emily. I see we have some people here that have experienced severe spinal cord injury, along with some caregivers, and certainly welcome to our students and researchers. And then we have some corporate representation, and actually the majority of you are here today to learn more about this type of research. So regardless of why you are here, thank you so much for joining us. Now, today's virtual expedition is about giving hope to people who have been told they will never walk again. And at the University Hospital Foundation, giving hope is the driving force that inspires everything we do. By continuously seeking solutions to complex health conditions and supporting the work of people like Dr. Vivian Mushahwar, we see ourselves as agents of hope. Thanks to the generosity of donors and corporate sponsors in the last 10 years, we've raised nearly $220 million in support of advanced medical care in our communities. Through strategic partnerships with government and industry, we are igniting research and innovation that may have impact around the world, beginning right here at the University of Alberta Hospital. Roughly 45,000 Canadians live with traumatic spinal cord injury, including about 1,800 new cases every year. Dr. Mushahwar will define for us exactly what traumatic spinal cord injuries are and how devastating they can be. But the numbers tell us that about half of all people who have won are told that they will never walk again. As you can imagine, such news would have debilitating consequences on their quality of life, their independence, and their mental health. Now, let's flip the script and consider what it would be like if you could tell these people that there is hope for them, that researchers at the University of Alberta are developing a spinal implant that may one day put them back on their feet again. Wouldn't it be amazing to be a part of something like that? Well, I certainly think so. And that's why we're here today, to learn about that amazing research project and the role that donors to the University Hospital Foundation can play to make it happen. To guide us through this fascinating journey, I would like to introduce to you one of our fearless Agent of Hope leaders, our Chief Cultural and Experience Officer, Amanda Radakovich. Amanda?
Thanks, Carolyn, and good afternoon, everyone. I'm so glad you have joined us because, as Carolyn said, today our virtual expedition is about giving people hope. I know you can say that many of the research projects we support give people hope, but this one feels a bit different. When we think about traumatic spinal cord injuries, we often think about a horrifying car crash, a near fatal fall, or a 5-alarm workplace accident. These are situations that most of us, we hope, will never have to deal with. To live through such an event is a miracle. What would it mean to you if you were told you would never walk again? Fortunately, there are people in our world who have the vision to see beyond what everyone else is looking at. People who have the willingness to try new things and the dogged determination to keep going despite setbacks and failures. Our guest today is one of those people, and whether she realizes it or not, through her research, Dr. Mushahwar is also an agent of hope for those who have experienced spinal cord injuries and for their families. Our role in this project is straightforward. Research takes money to pay for staffing, equipment, and technology, and access to brilliant minds whose input is vital in moving it from one step to the next. Community support is the difference between good healthcare and great healthcare, the margin of excellence that saves lives and inspires even greater hope for the future. I would now like to introduce our special guest. Dr. Vivian Mushahwar is a professor of medicine at the University of Alberta and the director of the Sensory Motor Adaptive Rehabilitation Technology, or SMART Network. She is also a Canada Research Chair in Functional Restoration. Dr. Mushahwar, we are so happy to have you with us today. The virtual floor is yours.
Thank you so very much, Amanda. Let me share my screen. I think you should be able to see my screen now. Is that correct?
Yes, everything looks great.
Wonderful, thank you. So Amanda and Carolyn, thanks so much again for the very kind introduction, and thanks to the University Hospital Foundation for the invitation to give this talk. It's really a great pleasure to be here today. Now, the overall goal of the work in my lab is to develop interventions that would improve function after neural injury or disease. And in today's talk, I will present my group's work in restoring the ability to walk for persons who have experienced a spinal cord injury. But before I start, I would like to acknowledge the incredible group of researchers that I've had the great privilege of working with over the past decade as part of the SMART network at the University of Alberta. And as Amanda said, SMART stands for Sensory Motor Adaptive Rehabilitation Technology. Our members come from many different disciplines, including neuroscience, engineering, cell biology, computer science, medicine, rehabilitation, health economics, social science, and consumer needs. And our mission is to develop intelligent medical devices and innovative rehabilitation interventions that significantly improve functional outcomes for people with neurological conditions. And here, we're talking about people who have experienced neural injuries or diseases, such as spinal cord injuries, stroke, multiple sclerosis, or Parkinson's disease. And our goal is to take these innovations to the clinic to improve quality of care and improve patient outcomes, while also reducing healthcare costs. Now, the focus of my talk today is on spinal cord injury. And as many of you may know, spinal cord injury is damage to the spinal cord, which lies within the spine or the back and the bones in our back. And as you can see from this zoomed image, a spinal cord injury can cause dramatic damage to the bone and to the spinal cord. Now, spinal cord injury can be caused by a traumatic event, such as a car accident. And in fact, vehicular accidents are the #1 cause of traumatic spinal cord injury. Now, this damage to the spinal cord can completely or partially disrupt the communication between the brain and the region of the spinal cord below the injury. And what this would result in complete or partial paralysis of all organs and muscles that are controlled by the portion of the spinal cord below the level of the injury. A spinal cord injury can also be caused by non-traumatic events, such as surgical procedures to remove a tumor that may reside on or within the spinal cord. Now, To give you a little bit of statistics on spinal cord injury in Canada, there's unfortunately more than 86,000 people living with spinal cord injury now, and about half of those have experienced a traumatic spinal cord injury. And every year, about 1,700 to 1,800 new traumatic injuries are incurred. And the unfortunate thing is that these injuries are mostly incurred in persons who are in the prime of their life, persons who are 16 to 34 years of age. And with the medical improvements in the management of spinal cord injury soon after the injury, people now with spinal cord injury are expected to have near normal lifespans. And as Amanda said, at least 50% of people with spinal cord injury never recover the ability to walk again. Now, what are the needs of persons with spinal cord injury? These needs are many, and they depend on the level and the severity of injury, keeping in mind that the organs and muscles controlled by the portion of the spinal cord below the injury are either completely or partially paralyzed. Now, for persons with injuries at levels high in their spine, the need to breathe independently and to be able to reach and grasp an object is very important. All persons with spinal cord injury experience various levels of disruption to their bowel, bladder, and sexual function, and all have disrupted cardiovascular function. People with spinal cord injury are highly susceptible to conditions that result from their reduced mobility and impaired sensation, such as pressure injuries, which were previously known as pressure ulcers or bed sores, and deep vein thrombosis, which are clots in the veins of the legs. And the vast majority of people with spinal cord injury would like to be able to stand and walk again. Now, the work in my lab focuses on addressing some of the needs of persons experiencing spinal cord injury. And this includes the activation of spinal networks, either through implantable or non-invasive electrical stimulation strategies to improve mobility. It also includes wearable neuroprosthetic devices to reduce secondary complications such as pressure injuries or deep vein thrombosis. And our work also includes combinations of electrical stimulation and exoskeletons to improve the lower and upper limb function. And for this talk, I will focus on the activation of spinal networks for improving walking after spinal cord injury. Now, one may ask, why focus on walking when the restoration of other functions may be more important? Well, we do that because in addition to the psychological benefits of standing upright, walking has numerous benefits that address many other needs. For example, walking improves bone health, muscle health, cardiovascular health, and bowel and bladder function. Walking also reduces the incidence of pressure injuries and the incidence of deep vein thrombosis. Now, for restoring walking capacity, our lab has been unique in focusing primarily on re-engaging and reactivating the neural networks inside the spinal cord. Now, for persons with partial spinal cord injuries, that is, persons who have some remaining connections between the brain and the spinal cord below the level of injury, we have focused on engaging neural networks throughout the spinal cord in a rehabilitation intervention that involves simultaneous arm and leg activation. For persons with more severe injuries, where there is clinically complete disruption in the connections between the brain and the spinal cord, we have focused on activating this region of the spinal cord that's called the lumbar region using micro implants. Now, focusing on persons with partial spinal cord injury, and despite the prevailing scientific knowledge regarding the importance of the arms, which move in coordination with the legs during walking, the arms have not to date been systematically involved in activity-based therapies for improving walking. And this slide and the next will show examples of two of the most common rehabilitation interventions used to improve walking capacity. The first intervention is known as body weight supported treadmill locomotor training. And what you see here is Ryan Strasnitsky, who's one of the Humboldt Broncos players who unfortunately was in that car accident that left him with a spinal cord injury. In this video, you see him undergoing this body weight supported treadmill locomotor training therapy, and this video came from his Twitter account. Now, as you can see, this intervention involves supporting the person. I'm not quite sure what's happening to the video. I'm going to see if it can play again. But you've seen the video, I hope, and you can see that the intervention involves supporting the person in a harness with their feet over the moving belt of a treadmill, and two therapists move the legs to match the speed of the treadmill belt, while a third therapist stabilizes the trunk. Now, this intervention has shown benefits, especially for persons with partial spinal cord injury. An alternative approach to this intervention is to use a robotic system for delivering the therapy. Unfortunately, the outcomes regarding benefits using the robotics have been mixed so far. But one of the things that we can see here is that not only do these interventions not engage the arms, but the intervention that has arguably shown most effectiveness is actually very labor intensive. So what we wanted to do is to find out if engaging the arms simultaneously with the legs is in fact a beneficial therapy. So we wanted to deliver an activity-based therapy that engages both the arms and the legs. And for that, we use simultaneous arm and leg cycling that allows coordinated rhythmic activation of the arms and the legs. And we applied electrical stimulation to the legs to assist with the generation of the movement. Now, this training intervention was delivered for about 12 weeks, and we found that it is actually quite effective in improving walking capacity in persons with partial paralysis. And what you see here in those videos is a study participant in the arm and leg cycling group before and after he received the therapy. Now, before training, you can see that the participant is hunched over, he's looking down, he's walking slowly, and he's putting a lot of effort into swinging his legs forward. After training, he's standing upright. He's no longer looking at his feet during walking, and that's because he has improved sensation that allows him to know where his legs are in space, so he doesn't need to look at where his legs are. And very importantly, his spasticity, or the uncontrolled contractions in his legs, has reduced. And he is able, as you can see, to walk much faster relative to pre-training levels. Now, the results of this pilot study were very encouraging. And when we compared the results to published work that focused on conventional gait-specific locomotor training, in other words, interventions that focus on the legs only, we found that the arm and leg cycling appeared to improve walking metrics at least 2 times more than what the current therapies show. So what this figure shows you, the bars over here, show the improvement in walking metrics that were reported by various studies that focus on training the legs only. And the dashed line over here shows the average improvement across all of these studies. And what you could see is that the arm and leg study has shown at least twice the amount of improvement in these walking metrics. Now, these results have been very compelling, that electrical stimulation assisted cycling is now applied in acute care soon after spinal cord injury. And this work is led by Dr. Chester Ho, who will actually be talking about this during the next University Hospital Foundation virtual exhibition. But collectively, we believe that this work provides a feasible, practical, and effective therapy that can accelerate neural recovery and improve walking capacity. Now, if we switch our attention to persons with complete spinal cord injury, here we have focused on harnessing the networks in this small region of the spinal cord called the lumbar enlargement. This small region is only about 5 centimeters long and is located just at the base of our back. And the interesting thing about this small region is that it contains a large proportion of the neural networks that are involved in walking. And in fact, this region is known as a spinal cord center for locomotion. Now, to understand where these neural networks are, let's look inside the spinal cord. And what we're looking at is a cross-section of spinal cord. We kind of cut the spinal cord this way and we flipped it around so we can look inside it. And you can see this typical shape of the spinal cord that is covered by different layers of tissue. This would be now your back, and this would be the front. And what we found out is that the locomotor-related networks in the lumbar enlargement reside in this region of the spinal cord, deep inside the spinal cord. So the question becomes, how do you activate them? Well, one way is to apply electrical stimulation to the back surface of the spinal cord, and an approach that is referred to as epidural stimulation. This is a surgical implant where a sheet of electrodes, which is what you can see over here, is placed surgically on the surface of the spinal cord. And you may have heard about this in the news, and it's actually similar to the implant that Ryan received by going to Thailand. Now, if we look back inside the spinal cord, we see the sheet of electrodes here in green and black that is on top of the surface of the spinal cord. And when electrical stimulation is applied, these regions over here of the spinal cord are activated, and then they indirectly activate the regions of interest through multiple pathways. Now, the use of epidural spinal cord stimulation to produce stepping was nicely demonstrated over the past 4 years by, my apologies here, I went too fast. Okay, so the use of spinal cord stimulation to produce stepping was demonstrated over the past 4 years by Susie Harkima's group in Louisville, by Kendall Lee's group in the Mayo Clinic in Rochester, and most recently by Gregoire Courtine in Lausanne, Switzerland. And the outcomes of this work are actually very impressive, especially when one keeps in mind that the persons that you see here in those videos, the persons who participate in these studies had complete motor injuries of the spinal cord and were unable to step over ground at all before the implant. Now, with the implant combined with varying levels of physical therapy, people were able to step over ground for about 90 to 230 meters, depending on the study and depending on the different stimulation strategy that was used. So this is very exciting. These results really show us what is possible in terms of activating the spinal cord. But our thought was that perhaps activating the locomotor networks more directly through micro implants that go inside the spinal cord perhaps would provide even better walking that allows people to walk faster and for longer distances. Now, for that, we developed a micro implant that allows us to deliver minute levels of electrical stimulation inside the spinal cord to activate elements of the locomotor networks. And now we're talking about an implant in this tiny small region of the spinal cord. This is a picture of what the implant looks like. It has microelectrodes that penetrate into the spinal cord to activate the regions of interest. And then these micro wires have leads that connect them to an implanted stimulator. And to give you kind of a big picture of what this implant is supposed to do, this tiny implant in this small region, which is now blown up in this middle here so that we can look at it, is supposed to deliver coordinated electrical stimuli through those micro electrodes in the spinal cord to activate different elements of the locomotor networks that are involved in walking and to produce overground walking. Now, this is a great idea, we thought, but the question is it sound? So to test whether this idea is sound, we performed extensive testing in a range of preclinical models to address multiple questions. And one is, how stable are these implants and how safe are they? Also, can these implants really produce functions such as standing, stepping, and overground walking? Could these implants truly restore these functions? So we've done testing in multiple, as I said, preclinical models. And what we found out is that in models where the implants were placed for many months, at least 80% of the microelectrodes in the implant continue to produce the same responses over and over and over again, suggesting that the implant is very stable. This was also verified through MRI images that demonstrated that the implants stayed in place. We also found that the microimplant causes minimal tissue damage, which means that it is safe. And we saw that it could produce long durations of standing with stable posture. And if we compare what the microimplant produces relative to other approaches, we saw that about 21 minutes of persistent stable standing could be achieved, while only about 4.2 minutes could be achieved with other interventions. Now, the question was, can we actually produce overground walking, and for how long? And the exciting thing is that, in fact, we were able in preclinical models to produce long distances of stable overground walking with the implant. And what you see over here on this axis is the distance of walking in meters. And you can see it goes up to 1,000 meters. This is a kilometer. And you can see here is the force that is generated during each step. And what you can see is that this is very stable throughout the walking distance of a kilometer. This is an unprecedented distance of walking with any intervention that is currently available. And we're so excited about this. Now, if you compare this to walking that's produced by other interventions, including epidural spinal cord stimulation, you could see that that does not last for too long. So these results have been very exciting and suggested that the spinal microimplant may be able to restore walking after severe spinal cord injury in people. And our focus over the past 2 years has been on translating this work to the clinic. And to do so, we have transitioned to using an animal model that more closely resembles humans, particularly from the perspective of the size and morphology of the spinal cord and the spinal column. And this animal model is the pig. So now, if we magnify the implant quite a bit, this is what the new implant now looks like. You can see that it has electrode tips that are de-insulated and sharpened. We have microcoils that are implants that are placed in the leads that are connected to each of the spinal cord to allow for the stretching of the spinal cord to take place without pulling out of the electrodes. We have a tap over here that provides added fixation to the spinal cord. And we have a coiled cable that accommodates the movement of the spinal cord relative to the bone where the implant is fixed. And as we move forward, we know that there will be many technological challenges, but we're hoping that we will be able to address those as we proceed with this work. So to wrap up the talk, I hope that I convinced you that engaging the spinal networks is an effective means for improving mobility after spinal cord injury. And really, arm and leg cycling is a safe and cost-effective approach to improving walking ability after incomplete or partial spinal cord injury. For persons with complete spinal cord injury, we believe that the spinal microimplant may reliably produce long durations of standing and long distances of functional walking. So now we're preparing this microimplant for first-in-human testing in persons with complete spinal cord injury. With that, I'd like to end by thanking the outstanding group of people in the lab who have done all the great work that I've shown today. I would also like to acknowledge our collaborators from the University of Alberta and beyond. I'd also like to acknowledge the funding agencies that supported this work, without which this would not have been possible. I would particularly like to point out the University Hospital Foundation through the generous support of Jim and Nancy Hutton, Leo Brock, and Michael and Angela Williams. Thank you.
Thank you, Dr. Mushahwar. That was exciting. Thank you for that incredible presentation. Like everyone here, I am very excited and looking forward to hearing more from you during this question and answer period. My name is Prince Osei. I'm a member of the development team here at the University Hospital Foundation, and I have the honor of being the moderator for the question and answer period. For our audience and participants today, there's a Q&A button at the bottom of your screen. Please just type in your questions, and I will read them to Dr. Mushahwar as they come in. We already have several questions here, so we'll jump right into it. But I do have a question of my own, Dr. Mushahwar. How or what is the role that animals play in your research?
Yeah, Prince, thank you very much for that question. This is a very important question, and animals play a critical role in our work. Now, you have noticed that in the first part of the work, this was non-invasive interventions. So that work could very quickly be tested in human study participants. But when the work becomes invasive, we are unable to move to humans, obviously, until we can prove that the work is safe, feasible, and effective, and are able to convince the regulatory agencies such as Health Canada that this is acceptable as a first step to test in humans. Without really providing that work from animal models and appropriate animal models that represent humans as closely as possible, such as pigs, we really cannot ever get approvals to move forward with this work. Our goal is to be very, very conscientious and use a minimal number of animals and provide them with the most comfort that we can provide, while we are trying to build the evidence that would eventually take us to human implementation.
Thank you. We do have one of our participants asking the following question. My injury is not that serious, but prevents me from walking comfortably. I have arthritis and it's affecting my spinal cord. They want to put screws and plates in my spinal cord where it is affected. Would you, Dr. Mushahwar, have an opinion on this potential treatment option?
Yes, in fact, this is called spinal fixation or spinal fusion. You'd be surprised that it's actually quite common, even in persons who are neurologically intact. There are multiple reasons why people would end up going for screws and rods that would stabilize the spinal column, and often that is good strategy for improving the health and reducing the risk of injuring the spinal cord more. However, having the spinal fusion does not prevent the person who was asked the question from participating in interventions such as arm and leg cycling. Obviously, we would need to get permission from the doctor to ensure that they are safe and we're not going to cause any damage to their implant. So they have to go through the surgery, they have to heal, and then get the okay to be able to participate in studies, and not just our studies. They would be able to participate and perhaps even improve their functional outcomes.
Excellent. So would your work help a young adult with cerebral palsy who has never walked?
That's another great question. And in fact, that is a group of persons with neurological damage that we are actually very interested in. And it just so happens that we're in fact preparing a grant application that would focus on children and adults with cerebral palsy. Remember, with the cerebral palsy, most of the injury is really in the brain. So we believe that we would be able to improve a lot of those circuits in the spinal cord, perhaps with arm and leg cycling to start with, and then one will see if there's a need for the micro implant in the future.
Okay. So our next question from Alaya is, what effects, if any, do the implants or the electrical stimulation have on the organ system innervated by the nerves below the level of injury, especially those placed a little bit higher up in the spinal cord? I know they were activating the motor network, but are there collateral effects simply due to their proximity to other damaged or blocked neural pathways? And the other question is also, or are the effects any selective to the locomotor nerves?
Okay, so the answer to the last part is no. The effect is not selective to locomotor nerves. It all depends on where you put the electrodes. So the spinal cord has compartmentalized function, right? So depending on where you go in the spinal cord, you will get different functions. So if you go to the cervical region, you may improve breathing, you may improve arm function. If you go to the thoracic region, you may improve blood pressure, you may improve posture and being able to sit upright in the wheelchair. If you go lower than where we were, so a little bit more below the region where we were stimulating, you could improve bladder function. So really depending on where you go, you can improve different functions. Of course, you can apply electrical stimulation outside the spinal cord as well, right? So you could apply it to, the nerves and muscles in the periphery. It all depends on what the function is that needs to be restored. But going to the question that if I understand it correctly, would the electrical stimulation cause more damage? That's not the case. We have not seen that. And in fact, there have been studies that demonstrate that electrical stimulation can actually improve neural regeneration. And our own Dr. Ming Chan here from the University of Alberta has done a study that shows that electrical stimulation, in fact, improves nerve regeneration after nerve injury. And there are other studies that would show that electrical stimulation could, in fact, improve spinal cord regeneration. So there seems to be more benefits than harms to electrical stimulation.
Wow. Thank you. Dr. Mushahwar, thanks so much for your lecture. This is from one of our participants. It is amazing, your research field and experience. I was wondering if these or those electrical devices that you showed us could be adapted also in people who suffer from myelomeningocele.
Yeah. So this would so remember that this inside look that I gave you of the spinal cord, and there are those tissues around, different types of tissues around the spinal cord, and one of them, and they're called the meninges, right? They're kind of protective layers around the spinal cord, and these could get inflamed. There are diseases of the meninges that end up causing damage to the spinal cord. It all depends. So if the condition is stable, there could be benefit from electrical stimulation, either non-invasive electrical stimulation or invasive if that's what is needed. All depends on what level of damage has been caused by this condition of the meninges around the spinal cord.
So we have a participant from Ecuador. I have a complete spinal cord injury, and I would like to know how can patients be part of your studies? Is there any way we can apply to be part of it?
This is Pablo, this is a question that we receive all the time. And our hope is that we can have anyone and everyone who could benefit from these interventions to be part of the study. Right now, the arm and leg cycling is something that is being implemented, is still in a research basis in persons experiencing spinal cord injury. The complete spinal cord injury, which is where the micro implant would come in handy, is not quite ready to be placed in human participants. We still need to do a bit of work, quite a bit of work, to be able to convince the health authorities that this is safe and this is feasible and effective. We're on our way to getting there. We've come a long way, and hopefully with support with the support that we've received from the University Hospital Foundation, from grants that we've secured from the Department of Defense in the US, hopefully we'll be coming closer and closer to getting those regulatory approvals that then will allow us to start working with persons with complete spinal cord injury. And hopefully at that time, we'll be able to invite you to be part of the study. Please stay in touch, and we'll keep you informed as of how we're progressing.
Okay. And that sort of is a great segue to the next question. How far are we from doing these trials in human beings? Few years, or is it a decade?
Yeah, you know what? In the past, I would always say 10 years. But right now, I'm seeing that we actually, there is a light at the end of the tunnel. The type of work that we're doing right now is critical to answering in preclinical models that resemble humans in many ways, whether these implants work. We had not been at this stage ever before. So we are at this stage now, which is very critical. And I now put about a 5-year limit to it, as to within those 5 years, 4 to 5 years, we will be at the doors of Health Canada, asking them what it is that they need from us to convince them that we can move to first in human testing. Now, they may come back and say, okay, what you've done is fine. Or maybe they can come back and say, we want you to show this, this, and that. And obviously we need to show this, this, and that. And then go back and hope to get approvals. So it's getting closer and closer, but it's not decades away as it had been maybe in the past.
Thank you so much. It's exciting. Victor is asking, how portable are the esteem devices? Can they be used outside the laboratory?
Yeah, hi, Victor. Thanks for the question. The electrical stimulation devices are quite portable. Now, the ones that come along with arm and leg cycling, these are actually built into the cycling device. So they're not portable. You need to move the whole cycling system with you. But there are systems that we use that are handheld, which we apply electrical stimulation to anywhere. And they could be, in fact, if you look at some of the stimulators that we developed for the sock to prevent deep vein thrombosis, they're actually this small. This is like about a third of your cell phone. So it depends on which electrical stimulation system you're talking about. They could be handheld, or they could be much smaller than that.
Okay.
The implanted systems, obviously, they're micro size, and they're all implanted inside the body, including the stimulator. Yeah, which is very small.
Wow. Jim says, hi, do you have a timeline to get to the point of an initial human trial? But his second question is that, what are your funding needs to get to human trials?
Jim, thanks for that question, and thanks for the incredible support and donations that you've made to this program. We really can't move forward without people like you, and we really appreciate it. So what is our timeline? So that goes back to about 4 to 5 years to be at the doors of Health Canada, right? And again, it all depends on what. I mean, we're not going to wait for 5 years before we talk to Health Canada. We will start the discussions probably in about a year or so, maybe 2 years. Latest, we'll start the discussions with them just to kind of get an idea of how we can shape our work so that it meets their needs. In terms of funding, that now is, first in human testing is expensive. This is because it involves getting medical grade implants that have to be prepared by a company. So we need to kind of contract resources for that. We need to be able to pay for the surgical procedure. We need to be able to pay to the personnel involved in the project, the physiotherapists, right, the physiatrists, so the researchers who would be collecting data. So it becomes very heavy in terms of personnel. So a clinical trial of this sort probably would need anywhere between $5 to $6 to $7 million to get testing going. Again, it's to pay for all of these needs, assuming that Health Canada doesn't want more and more experiments to be done, but hopefully we'll be able to manage that.
Thank you. Edgar is asking, how long after the trials of the implants for individuals with complete spinal cord injuries would a trial of the implants be available for individuals with incomplete injuries, or would both trials be able to run simultaneously?
Yeah, hello, Edgar. We will not run them simultaneously. So there is a reason why we're starting with complete spinal cord injury, because this would be the first time that we tackle walking with these implants. Now, we already know that similar implants were actually placed in the spinal cord of human study participants for the purpose of restoring bladder function. So we know that we have a little bit of understanding about safety, but no one has done this in the lumbar region with the kind of implants that we do. So we start with complete spinal cord injury, just to make sure that we are not causing additional damage and causing loss of residual function. Okay, we haven't seen that in our preclinical models, but we would need to do that first. And I think Health Canada would not allow us to move to incomplete spinal cord injuries until we prove that they are safe, feasible, functional in persons with complete injury. So I would assume that that's not going to be, this is where I would say it's not going to be probably until 10 years from now to move to incomplete spinal cord injury.
Thank you. And I have a question myself. Have you received interest from other universities, research institutions, or hospitals in this phenomenal work?
Yeah, thank you so much. We're really the pioneers in this area, and there's been a lot of interest. So we've translated this knowledge and trained people at various universities in the US to use the approach, those micro implants, to restore other functions. For example, at the University of Washington in Seattle, they're interested in looking at upper extremity function. At the University of Florida in Gainesville, they're interested in seeing if these implants would work for improving respiration in people who are dependent on a ventilator to breathe, just because the spinal cord injury is so high. So there are other groups that are looking into this, and all of them have been based on, we are translating that knowledge to them. And it's great to have more and more people working on this, because one lab cannot do it all. And if you have other labs and other universities invested in looking at other functions, that's fabulous.
Fantastic. Is it a divide and conquer?
It's divide and conquer,
Yeah.
and it will be for the benefit of, obviously, persons experiencing spinal cord injury in the future.
Right. Kenrick is asking, would the electrical signal from the implant stimulate and eventually heal the spinal cord to some extent?
Yeah, that's a very interesting question. We have not, we have anecdotal evidence from our work and from the work of others, but we have not done a particular study that looks at that. There are multiple reasons to believe that that will be the case, because electrical stimulation of peripheral nerves had improved and accelerated recovery and regeneration of those nerves. We think that some similar mechanisms could also work in the spinal cord. We have to test it out, though.
Is microimplant helpful in managing spasticity in animal models?
Yeah, Srijana, thanks for asking the question. So spasticity comes in different forms, but it's really uncontrolled contractions of muscles, right? These are contractions that are not under the control of people, and they interfere with the movements, and they could actually be painful for persons who have incomplete spinal cord injury. So what we have found out with the microimplants in our preclinical models is that had spasticity, that indeed, once you turn on the stimulation, spasticity is gone. Okay. Now, when you turn off stimulation, it comes back. But what we have not done the studies to see how much stimulation is needed and for how long to keep spasticity. Like to reduce spasticity quite a bit and to prevent it for long durations. That is yet another set of questions that we'd like to be able to answer. But we have direct evidence that turning on the stimulation stops the spasticity completely.
Pablo is again asking, the fact that the patient has electrodes in their body, would they be excluded criteria for the studies, or even if they can be removed?
It depends on where those electrodes are, what region is targeted, how much, what was the nature of those electrodes. If those electrodes were on the surface of the spinal cord, maybe that would be fine. We are aiming to make sure that the micro implants cause such minimal damage that if you need to upgrade the implants because there are better technologies in the future, you can remove the old implant and you can put a new implant in the same location. But what's very critical is that tissue remains viable. And that means that's part of our safety study so that when we go in and remove an implant, we can put a new implant in the same region.
Excellent. Where does the electrical, Victor is asking, the electrical stimulation come from? How is it generated?
So maybe I can describe that for the two studies that I showed, but the concept is the same. There is a stimulator. The stimulator can be, as I mentioned, a handheld external device with the leads or wires that connect to electrodes that are placed on the surface of the skin. That's the handheld system, and that electrical current is generated within that stimulator and sent through the leads to the electrode to cause the muscles to contract. For the micro implant, it's the same concept. There is a very small stimulator, very, very small stimulator that is implanted under the skin, and that is connected to the implant that is in the spinal cord. And then you use an external coil, as it says, a transmitting coil. It's just a coil, right, that gets placed on the surface of the skin, and that transmits wirelessly the commands to the stimulator so that the electrical current can be generated and sent to the microimplants to activate the networks in the spinal cord. And in terms of maintained, that electrical stimulation is maintained through the stimulator. So the stimulator has to be active to be generating those electrical currents.
So another question from James: can you give some more detail on the coming steps?
Yeah. So now we've identified our animal model that would be necessary for doing and testing the human-like micro implant. We have now prototypes of this implant, which we developed despite the pandemic, and we're able. It took a little bit of time to get the necessary equipment to do that, but we have done that. Now these implants pass the tests on the bench. Okay, we still need to be so. In other words, before we put them in the pigs, we still need to do a little bit more testing on the bench to demonstrate that they are mechanically stable. We know that they're electrically stable. We want to make sure that they are mechanically stable because they're just so fine. I mean, we're talking about implants that are smaller than the human hair. They're just so fine. And I guess I should have mentioned that during the presentation. These are really fine implants. So we want to make sure that they are mechanically stable. And then we're going to put them in our animal model, and we need to be able to do the testing for at least 6 months, if more, to demonstrate that these implants are stable for long periods of time. Okay, we need to be able to collect a lot of data from these models, looking at their walking, looking at their muscle activity, looking at all sorts of things, right? And document all of that. Obviously, need to understand whether there's any damage to the spinal cord, and that would have to be assessed very, very carefully to look at the health of the tissue around the spinal cord. So these are the steps that we are working on for the next 3 to 4 years to be able to get together all that evidence. I'm not seeing Jim's question. What was maybe you can remind me of the question again, just to make sure that I've answered all parts of it.
So yeah, he asks about more details for the next steps. Right.
Yeah. So all these data will be put together, and we'll and along the way we'll be talking to Health Canada to get a better and better understanding of what needs to be done, so that they will be able to approve our application to go for first in human testing. There are a lot of things that are involved. So, for example, the testing, not at this stage, but another stage, the testing has to be done under what's called good laboratory practices. This is now regulatory practices that require detailed documentation of factors that are not always documented. But this is what we need to be able to start doing. It takes time, it takes effort. We're going to do it, and hopefully our findings would be that this is viable, and that's really the most critical thing. I think the next 3 years are just critical. Is this viable? Is this really viable in an animal model that truly represents or very closely represents humans? If it is, then we're good. We're good. Yeah.
Dr. Mushahwar, let's get it done. Let's
get it done.
Yeah. Thank you to our participants. That is all the time we have for the questions today. I will turn over to my colleague, Caroline.
Well, thank you, Prince. And wow, what an amazing and promising journey we've been on today. And I hope our audience has enjoyed this as much as I know we have. On behalf of the University Hospital Foundation, including Amanda, Prince, Emily, and myself, and of course, our very, very special guest, Dr. Vivian Mushahwar, thank you for your time and active participation. Within the next few days, we will send you the recording from today's expedition, and please feel free to share it with your friends and family. If you'd like to learn more about us, please reach out by email or visit our website at give2uhf.ca. Our next virtual expedition will take place on November 16th and will feature Dr. Chester Ho as he shares more about neurological rehabilitation, which is this year's cause for Festival of Trees. And by the way, we're returning live this year. Please visit our website for more details and exciting updates. Now you can watch recordings from our past virtual expeditions on the University Hospital Foundation's YouTube channel. And as Amanda mentioned earlier, ongoing community support is vital to ensuring that the work of innovators like Dr. Mushahwar can continue to make breakthrough advancements in patient care and improve health in the communities we serve and around the world. Thank you so much for joining us today. And finally, we leave you with a short video entitled Ignite 2030. Have a wonderful evening, everyone.